All right, what's up, guys? We're going to go ahead and get started with this Newton's Law of Gravitation worksheet. I'm just going to go ahead and work through a few problems here to help you guys out so you can see kind of how these new equations work. So the first one I want to talk about is number 1 right here. It says a person of mass 70 kilograms is standing on planet X. So you'll see all these X's on this worksheet. That's just because I want you guys to pick any X value and it will give you some sort of planet and some other values. I'm going to go ahead and choose my X value to be 6. So that's going to give me the planet Mercury and all of this information for this first part. So I'll go ahead and write Mercury here just in case you skipped the part where I said it. So number 1 says, use the universal law of gravitation to calculate the person's weight force on the planet. So the universal law of gravitation is Fg equals big G times m1 times m2 all over r squared. So if our planet is Mercury and we have a person's weight on that planet and we know the person's mass, let's go ahead and list out our variables, okay? So big G we know because that is a constant value. It's up here, right? It tells us that big G is 6.67 times 10 to the negative 11th. So M1 can either be the person's mass or the planet's mass. And I'm just going to go ahead and make it the person's mass. So M1 will be 70 kilograms. M2 will be the planet's mass. And since our planet is Mercury, it tells me right here the mass of that planet is 0.33 times 10. That's what that E stands for, to the 24th. R is going to be the distance from the center of that planet to the person. Well, the person's standing on the surface of that planet. So since they're standing on the surface of that planet, we're going to need to use this value right here, the diameter of the planet. But we need to remember that the diameter is the entire thing from one surface to another. So we don't need all of the diameter, we just need half of that value. So my R is going to be 4,878. And another thing to notice is that this is in kilometers, so we need to convert it into meters. So I'm going to go ahead and tack on 3 more zeros and then just divide by 2 to get the radius. All right, now that I have all my information, I can just go ahead and plug it into my equation, and I'll do that really quickly. I see that I get force gravity is equal to big G, which we said is 6.67, times 10 to the negative 11th, times m1, which is 70, times m2, which is 0.33, e to the 24th, all over 4,878,000 divided by 2 squared. I know this looks like a lot, but just make sure that when you're plugging this into your calculator, you just put parentheses here and parentheses on the bottom, and you should be good to go. Once you do that, you're going to figure out that the force of gravity that this person feels, or the weight force on that planet, should be equal to 259 newtons. All right, the next question says, use the universal law of acceleration to calculate the person's acceleration to that planet. So that one is going to be this equation right here, because that's the only one that has acceleration in it. And I'm just going to go ahead and write it down here. A equals big G times m over r squared. The thing to note here is that it doesn't tell us which m this is, and it doesn't tell us which r this is. But we can go ahead and use some reasoning to figure it out. So when we're talking about the acceleration equation, we also need to remember that it's the acceleration due to that planet. Since it's due to that planet, we're going to end up using the planet's mass here and the planet's distance from its center to its surface. So if I plug my numbers in now, I get A is equal to G. I'm just going to leave it as G instead of rewriting it every time, times the mass of the planet, which is 0.33, e to the 24th, divided by, and then again, this value right here, this r squared. And that's 4,878,000 divided by 2 squared. Again, make sure you put the top in parentheses, divide it by the bottom, and you should end up with an acceleration somewhere around 3.7 meters per second squared. Number 2 says calculate the force gravity between the sun and your planet. So again, I have my equation for force gravity. I'll just take it from above. Force gravity equals big G times m1 times m2 all over r squared. I know what the mass of my planet is. It's right here. I just used it. But now I need the mass of the sun. And the mass of the sun is just going to be equal to this number right here, because that's in our table and it tells us the mass. So I'll go ahead and copy that number down. 1.989 times 10 to the 30th kilograms. And then the R value, or the distance from the center of my planet to the center of the sun, well, they'd give me that exact value here. And that's going to be 58,900,000. But we need to realize that this is in kilometers. So since it's in kilometers, to convert it to meters, I'm going to go ahead and tack on 3 more zeros. And when I'm tacking on 3 more zeros, that just means that I'm multiplying by 1,000. Next, I'll plug this into my equation. Fg equals big G times m1, which we said was 0.33 e to the 24th, times m2, which is 1.989 times 10 to the 30th, all divided by 57,900,000,000,000. And don't forget that we need to square this number. Again, just put the top in parentheses and divide it by the bottom, and you should be good to go. You find out that your force gravity felt between the sun and your planet should be 1.31 E22. And since it's a force, it should be newtons. Quick question, which one feels this force? Is it the sun or is it your planet? It's a trick question. They both feel this force. All right, let's go ahead and look at number 3 now. Number 3 says you have a mass of x times 20. Remember, my x value was 6, so that's going to be 6 times 20. So my mass is going to equal 120 in this case. And you are being attracted to a new planet with a force of 500 newtons. So I'm feeling a force of 500 newtons towards that planet. If I was 7.1 times 10 to the 7th meters away from the center of the planet, what would the mass of that planet be? So basically it's saying my R value is 7.1 E7. Cool. So here's our equation, and we have to get used to this equation because we're going to be using it a lot. Fg equals G times M1 times M2 all over R squared. What I recommend here is that instead of plugging my numbers in and then solving, I recommend solving for the variables first and then plugging your numbers in. So what I mean by that is that it's asking me to solve for the mass of my planet. So I'm just going to manipulate this equation to solve for m. So if I do that, I'm going to go ahead and multiply this R2 over, and I get Fg times R squared equals big G M1 M2. Next, I'm going to go ahead and divide by big G and M1. And I get M2 is equal to our force of gravity times the distance from the center to the other center squared divided by big G times M1. And then I just go ahead and use this equation to solve for my answer. Doing so, I find out that the mass of my other planet should be 3.15 e to the 26 kilograms. All right, let's keep moving along. Number 4 says you have a mass of 20 times x. Again, my x value was 6, so my mass in this case is going to be 120. And you are standing 1.5 meters away from your favorite teacher, Mr. Denny. So that distance is going to be 1.5 meters. It tells me that Mr. Denny's mass, so my second mass, is 70 kilograms. It wants me to calculate the force of gravity between me and Mr. Denny. All right, and then I know what big G is. I'm not going to write that down, but I do know what this is. It's always the same, and it's right here in my equation as well. So I just go ahead and write down my force gravity equation. Force gravity equals big G times m1 times m2 all over r squared. I can plug my numbers in if I want. I get force gravity equals big G times 120 times 70 divided by 1.5 squared. I do the math, and I figure out that the force gravity between me and Mr. Denny should be 2.5 e to the negative 7th newtons. Let's move on to the next one. We'll notice, right, that this force gravity is very, very small, which makes sense because I'm not flying towards the person next to me. If this number was huge, right, like something that we're used to, like my normal weight of maybe 600-700 newtons, then maybe I would be flying towards that other person. But in this case, this number is so tiny that it has no effect on me, essentially. All right, let's take a look at number 5 now. It says the force of gravity between you and your sweetheart is x times 10 to the negative 7th. If your mass is 70 kilograms and your sweetheart's mass is 60 kilograms, solve for how closely you two are standing next to each other. So we could probably just skip this question for some of you because unfortunately you don't have that sweetheart. But we're just going to go ahead and pretend because, it will happen one day. All right, you will find that love of your life and it will be amazing and you'll be able to calculate the force of gravity between you and that special person. So if we look at this question, it says that our force of gravity is x times 10 to the negative 7. So my x was 6, so my force of gravity is just 6 e negative 7 newtons. The mass of my sweetheart is 70 kilograms, or that's my mass, it doesn't matter which one. M2 is 60 kilograms. And then distance, we don't know, okay? It says, would a chaperone at prom allow you to be that close? Well, we'll find out in just a sec. So here's our equation, just like before. Fg equals g times m1 times m2 all over r squared. I want to solve for r though, so I'm going to manipulate this equation to do that really quickly. I'm going to go ahead and multiply r over. So I have r squared over here. This r is gone, right, because it went over there. So now I have r squared times Fg equals big G times m1 times m2. Next, I'm going to go ahead and divide by Fg so I can get rid of this guy. And then I just have r squared equals G times m1 times m2 over Fg. Some of you are going to realize that I don't want r squared, I just want r. So I'm going to go ahead and square root both sides. By doing that, the squared goes away, and I'm just left with the following equation. R is equal to the square root of big G times m1 times m2 all over Fg. Now, all I have to do is just plug my numbers in and get my answer. So when you guys do this, make sure that you are using parentheses in your calculator, okay? And you should end up with an answer of 1.46 meters. I would say that any prom chaperone in their right mind will probably allow you to be 1.46 meters apart. That's pretty far away from your prom date. And if we remember, right, if we're doing our unit conversions and stuff, that's roughly around like 4 feet. So it doesn't even sound like you're dancing with that person. Perhaps maybe get a little bit closer, and then that force gravity will increase a little bit, and who knows, maybe that sweetheart of yours will turn into your soulmate and you'll start a beautiful family. You never know, all right? But you got to be closer if you want more attraction. All right, number 6. Two objects m1 and m2 are a distance d apart. The force of gravity between them is Fg. What will the new force of gravity be between them if blank? So these questions are about manipulation. And we need to take our equation and look at it really quickly to see how changing one of these variables is going to impact our force of gravity. We already talked about how if we increase mass, we will increase force gravity. And how if we increase distance, we will decrease force gravity. So we already know that these things are going to happen, and we can use these general statements to make sure that we're on the right track. So the first one says M1 is doubled and M2 increases by a factor of X. My advice to you guys is whatever is not mentioned in this problem, just set it equal to 1. So if I look at my equation, G isn't mentioned, G can just be 1. M1 is mentioned, M1 is doubled, so I'm going to make that 2 because it's 2 times as big. And don't forget my X value is 6. M2 is also increased, and that's by 6, so I'm going to set that to 6. And then divided by R isn't mentioned, I'm just going to set that to 1. So I just multiply everything through, and I figure out that my new force gravity is 12 times as big. Piece of cake. Do the next thing for number 2. Same thing, G isn't mentioned, M1 is doubled, so that's 2, and M2 decreases by a factor of 1 over X. So that would be 1 over 6 this time. Doesn't mention R squared, so just leave that as 1. I find out that now my force gravity has gotten smaller because one of the M's has doubled, but the other M has shrunk. Therefore, my force gravity in this case is just 1 times 2 times 1 over 6. That is 1/3. Letter C, same thing. M1 doubles, so this is 2. It doesn't say anything about M2, so I'm going to leave that as 1. And then it says the distance between them increases by a factor of 6. So I increase it by 6, but I need to remember that it's squared. So if I continue this, I end up with 2 over 36, meaning that my force gravity now is 1/18 as big, which makes sense, right? I'm increasing my distance, and since my distance is increasing, I would expect the force of gravity to get smaller. As distance increases, attraction decreases. Lastly, we have M1 doubling again. Doesn't mention M2, so just set that equal to 1. And this time it says that our distance decreases, so I'm going to expect a bigger force gravity. How much does it decrease by? 1 over 6. Again, we can't forget that distance is squared. So we really end up with 2 divided by 1 over 6 squared is 1 over 36. So if I plug this into my calculator, I can get it, but also I can just get it in my head too by flipping it. I end up with 2 times 36, because 2 over 1 over 36 is 2 times 36, and that gives me an increase of 72.